We're given the maximum allowable stress, 150 megapascals. Every piece of the truss has the same cross-section. 20 millimeter diameter is the bars. So the diameter is going to be 0.02 meters. I'm going to base units here for the calculation. This will be easier. I'll say 20 times 10 to the negative third meters will be an easier way to represent it. And we are looking for, again, what's the maximum value of P we can apply so that in none of the members does the stress exceed 150 megapascals, whether that's tension or compression. So if we start with that external picture, we're applying that force P up top. We have 1.5 meters. We have 2 meters. As we said, this is statically determinant. B is a roller. A is a pin, so we have an AX and an AY. I'm not going to go through all the equation details since we've done those to death in EMCH 211, but we solve some forces in the X, some forces in the Y, and we can find AX, AY, and BY. What we want is everything in terms of the applied force P. So if we solve AX, AY, and BY in terms of P, we're going to get that AX must be negative P. AY, we're going to get a negative 0.75 P. And BY, we're going to get as positive 0.75 times P. Yeah, I want everything in terms of P because ultimately I'm going to need to find the stresses in terms of this unknown value P. With the external forces, I can now move on and find my internal forces, either method of sections or method of joints. Really, they're going to look exactly the same in this case because there are only 3 members. So if I look at point C, for instance, if I do a pin diagram on point C, I have that applied force of P. I'm assuming tension in my members. I'll have the force in member AC. And I'll have the force in member BC. And this is Hibbler, so they love to use 3, 4, 5 triangles. We see that this is a 3, 4, 5 triangle. So it's 3 high, 4 long, and the hypotenuse is 5. From picture at C, I can now find the internal forces in terms of that applied force P. So I can find the value of FAC, the internal force in member AC. FAC is going to be 0.75 times P. And the force in BC, I'm going to find is negative 1.25 times P. Again, this is just coming from summing forces X, sum of forces Y. I'm concerned that all 3 of my members do not exceed this stress limit. So I need one more picture. I can draw B to find the internal force in the last member. So on point B, I have BY, which I found was 0.75 times P. I have the force in AB to the left. and then the force of BC up and to the left because I already made the assumption of tension, or I'm always making the assumption of tension. So it's pointing in this direction also at that same angle, 3, 4, 5. So finally, if I sum forces, say, in the x direction, I can get FAB is going to be equal to P. So the three internal forces, 0.75 P, negative 1.25 P, this will be in compression, and FAB is equal to P, which is going to be in tension. So I have all the internal forces in terms of that applied load P. So where can I go from here to answer the question, what's the most the value of P can be so that none of the members are exceeding that value of internal or of normal stress? The stress in this case is P over A. It has to be equal to, we're finding the limit of it, so we're going to set it equal to 100, it depends, plus or minus 150 times 10 to the 6th pascals. Now, what advantage do we have in this that in general we might not have? That's going to make this process simpler.
A is constant.
Right, all three of them have the same cross-sectional area. If they potentially we're going to see problems where they don't, and you really do have to do this one for each member. But since they all have the same area, which one member is the only one we really have to test? Yeah. Right, FBC is the only one because it has the most. Now it's going to be in absolute terms the most. These two are in tension, this one's in compression, but it's 1.25 versus 1 versus 0.75. So what we're going to say is that if BC is just on the limit of reaching its maximum, FAC and FAB are going to be below that maximum. But keep in mind in general, we could say that if, first of all, if they're made of different materials, then the maximum stress in each might be different. If they have different cross sections, then this area might be different. So this is a special case where we can get away with only testing one of them. But in general, we might have to test all of them to make sure, find the p-value for each, and see what the minimum is. In this case, though, we only have to test FBC. So we know that because it's in compression, we want to make sure we don't exceed negative 150 megapascals. And that's going to be equal to negative 1.25 times P over its cross-sectional area. I'll write this in base units. In this case, they are circular cross-sections. We were told they have a diameter of 20 times 10 to the negative third meters. That came from 20 millimeters. So the cross-sectional area we're going to test is pi times 20 times 10 to the negative third squared over 4. This is negative because it's in compression. This is negative because the force told us it's in compression. We will get a positive value of P out of this procedure. Solving for P, we get 37.7 times 10 to the third. We are working in, here we're at pascals. Pascals is going to be newtons per square meter. This is in square meters, meaning that P is going to be in newtons. So 37.7 times 10 to the third newtons, which is going to be the same as 37.7 kilonewtons.